Welcome back to today's lesson. We're still in Unit 11.1 on acids and bases. Today we're going to be looking at titrations. All right. So today this is the lesson for Tuesday, the 31st of March. So we had two papers to look at today. Stoichiometry. We're going to hit stoichiometry yet again, and then also the assignment. So your homework for today was to complete the pH and the POH assignment from yesterday. I am going to collect that, or I was, so be aware of that. So when we get back to school, we will be taking care of that. Make sure you've checked your answers with the answer key that I posted on my Canvas page. Make sure that you do that. If you have any questions, as usual, just let me know via email. So this is our last lesson on acids and bases, and so we will be looking at titrations and then going on to Unit 11.2 in our next meeting. All right, so let's screen up here. So titration. So a titration, and you should recall having done this in Chem 1. Probably not to the degree that we're doing it here, but at least I think the method should be familiar to you. So a titration is an analytical method in which a standard solution of known concentration is used to determine the concentration of another solution whereby its concentration is unknown. In an acid-base titration, which is the most common type, the reaction is an acid plus a base yield a salt and water. That should look familiar to you. That is, of course, a double replacement reaction, and in particular, an acid-base neutralization reaction. So during a titration, a solution of known concentration, which is called the standard solution, is put in a burette. So here I have a burette. Hopefully you can see it. And what I have in here is a predetermined concentration of hydrochloric acid in here. It's actually, I believe, 1.0 molar. And so that is in the burette. The solution of unknown concentration is put in a flask underneath the burette, and a small amount of indicator is added to it. An indicator is a solution that exhibits different colors in the presence of an acid as compared to a base. So what I have here, since we have the acid in our burette, our unknown concentration solution is basic. This is a concentration of sodium hydroxide. And in the presence of a base, the indicator I'm using is phenolphthalein, and it should appear a bright pink, which it does. I'll swirl that a little bit, and there we have that. As the unknown solution is constantly stirred, the burette is opened and the standard solution is allowed to mix in with it. Eventually, a color change permanently occurs, and at that point, where the addition of a single drop of standard solution causes a permanent color change in the unknown, the end point of the reaction has occurred. The end point, which is also called the equivalence point of a titration, is the point at which the number of moles of acid and the number of moles of base are equal. Okay, so I'm just going to briefly show you a demonstration of how that works. I'm probably not going to hit the exact equivalence point, but that's okay. I just want you to see what it looks like. So I'm going to release acid in there and constantly agitate the flask. And as we continue to add acid, I'm going to take a little more than that. I did not do this ahead of time, so we'll see. Uh-oh. Uh-oh. And there she goes. All right. So I ran it a little past, which for calculation purposes is not all that good. However, when we do titrations in lab, that's normally the way it's done. We do a first run to get a general idea of where the volume of acid that we need. And as I look here at the burette, it took about 12 mLs, give or take. So what we normally then do is do a second and a third trial, whereby now we have an idea of where the equivalence point is. And so when we do it the second and third time around, as we get close to that volume, what I would do, I'll just demonstrate that. What I would do is slow the release of acid down to a crawl, basically, where it's going drop by drop, and then keeping that thing constantly agitated. You'll be able to catch the exact drop where it goes from pink to colorless, which gives you then a much more accurate volume. So normally the procedure is we do one trial to get a general idea, throw it out, and then do two more trials and average those two, and that usually gives us some pretty accurate results. So I'll set that over there now. That wasn't too bad considering I threw it together in about 30 seconds. So anyway, let's go on to the next page. To calculate the concentration in molarity, remember, of an unknown solution by titration, a specific form of stoichiometry is utilized. So you have your stoichiometry diagram handy. This looks very, very familiar to solution stoichiometry, which we did not very long ago, just a little bit different twist at the end. So we're dealing with volumes now. And so we start with the volume of our known. That is our standard solution. In this case, it would have been HCl. We go to moles in step 2 using molarity, just like we do in solution stoichiometry. Step 3, of course, is always the same. That's the mole ratio between our unknown and known. And then step 4 is a little different here. So step 4 really looks like an inversion of step 1. In step 4, we have the volume of our unknown on the bottom in liters and 1 on the top, which seems odd, except when you look back at step 3, everything is canceled up to the moles of the unknown. We put the moles of the unknown here over the volume of unknown here, and that gives you an answer in moles per liter, which is, of course, molarity or molar. And so, again, step 4 is a little bit different, but essentially, stoichiometry is stoichiometry. We're doing essentially the same thing. So we will look at these two examples here, and then we'll be done. So this wants to know the concentration of 25.0 mLs of acetic acid if it was titrated to the end point by 15.0 mLs of a 0.500 molar solution of sodium hydroxide. So first things first, we're going to need our volume in liters because of molarity. So if we do that little conversion there, it'd be 0.0250 liters. Same thing with sodium hydroxide, 0.0150 liters. So now let's look at what we have here. First of all, of course, we need to balance the equation before we do anything. And this particular equation is balanced. Okay, already. And so what do we have? Well, we have 0.500 molar NaOH and a volume of 0.0150 liters. So that's our standard solution. We know its molarity and its volume. We have a volume of acetic acid, 0.0250 liters, but we have an unknown concentration. So again, that is our unknown. This would be our standard solution. This would be our unknown. So we set up the stoichiometry. We start with the volume of our known in step 1, just like we do with solution stoichiometry. So we have 0.0150 liters of NaOH over 1. We're going to convert that to moles using its concentration, its molarity. So it would be 0.500 moles of NaOH in 1 liter. Remember, molarity is moles per liter. Mole ratio here is 1 to 1. So 1 mole of acetic acid over 1 mole of NaOH. And now this is step 4, the one that's a little different. Now just a 1 on the top there, and now the volume of our unknown would go here. So we have 0.0250 liters of acetic acid. And again, I want you to see that these two units do not cancel. We don't want them to, because this is the moles of acetic acid over the liters of acetic acid, which then is its concentration in molarity. And so if you do the math to 3 sig figs, we have 0.300 molar of acetic acid. So that is the concentration of our unknown acid. Number 7, what is the concentration of 15.0 mLs of sulfuric acid? So again, that would be a volume in liters, 0.0150 liters, that has been titrated to its end point by 60 mLs of 0.200 molar potassium hydroxide. So in liters in volume, 0.0600 liters and 0.200 molar. So again, if we identify what we have here, we have a concentration of our potassium hydroxide, 0.200 molar. We have its volume, 0.0600 liters. H2SO4, we have its volume, 0.0150 liters, but we do not know its concentration. So this is our standard solution of known concentration. This is our unknown. Before we do the stoichiometry, we need to balance this one. This one does require a 2 in front of KOH and in front of water. So if we set up the stoichiometry steps, so we start with the volume of our known, 0.0600 liters of KOH, put it over 1, and then that would be, we use its molarity to get it to moles. So we have 0.200 moles of KOH over 1 liter of KOH, that's its concentration. Mole ratio now is 1 to 2. We have 1 mole of H2SO4 to 2 moles of KOH. And then again in step 4, we want to put a 1 up top. Remember, this looks like an inversion of step 1 here. 1 on the top, and now the volume of our unknown, 0.0150 liters of H2SO4. And once again, we don't want these to cancel. This is the moles of our unknown over the liters of our unknown, which then gives us its molarity. And rounding that to 3 sig figs, excuse me, 0.400 molar H2SO4, 0.400. So remember that in acid-base titration, essentially what we're doing is a neutralization reaction. Remember, it's double replacement. It's an acid-base neutralization reaction. And if you recall, double replacement reactions of any type are never redox, but they do have a net ionic equation, all right? And so if we look at that, and hopefully you would remember, then anything that's aqueous would get split into ions. So this would be 2 hydrogen ions and a sulfate ion. This would be 2 potassium ions and 2 hydroxide ions. This would be 2 potassium ions and a sulfate ion, and the water remains intact. And so based on that, our net ionic equation for this last one here would be 2 hydrogen ions and 2 hydroxide ions, yielding 2 waters. All right. In this one up here, with the being balanced, same net ionic equation, but now this would just, the 2's would be gone. It would just be 1. We don't use 1's. But the net ionic up here then would just be the same thing. minus the 2's. Remember, that's going to be the net ionic equation for any acid-base neutralization reaction. And of course, based on that, when you end up with a neutral solution after you titrate the acid with the base, you're taking an acidic solution and you put an equivalent number of moles with the basic solution. And so since the moles of each are the same, then you should get a pH of right at 7. Okay. That concludes our lesson, not only today, but for this unit. Again, you have a titration assignment. It is not very long at all. In fact, it's 6 or 7 problems, I believe. So that would be due tomorrow. And until next time, if you have any questions, let me know. Send me an email, and we'll catch you on the next lesson.